Hi students, in this video we're going to start chapter 5, Functions and Relations. So I've broken this chapter into the following 6 sections. We're going to start with an introduction to functions and relations. Then we're going to spend some time just on functions. We're going to look at one-to-one, onto, and inverse functions. Then we'll look at relations. Then we'll look at reflexivity, symmetry, and transitivity. And then we'll end with some modular arithmetic. So section 5.1 is just an introduction to functions and relations. So our goal for this section is to discuss definitions of functions and relations. So we first discussed the Cartesian product in section 4.6. So just a reminder, the definition for a Cartesian product is the following. The Cartesian product of set A and set B, which we symbolize this way and read as A cross B, is the set of all possible ordered pairs of the form AB, where A is an element of set A and B is an element of set B. So if we have R cross R, this is going to be your Cartesian plane. You're just going to think of it as your XY coordinate plane, because you're taking the set of real numbers, crossing it with the set of real numbers. And this is our definition for a function. So we're going to let x and y be sets. A function f from x to y is a subset of the Cartesian product x cross y, having the property that for each element x in the set of x, there is exactly one element y in the set of y, with the ordered pair xy being an element of the function. And sometimes we denote the function f from x to y using this notation here. The set X is called your domain for the function, and the set of all elements Y such that the ordered pair XY is an element of the function, which is a subset of Y, is called the range of the function. And our definition for a relation, we're going to let X and Y be sets, and a relation R from x to y is a subset of the Cartesian product x cross y, and given an ordered pair xy in that Cartesian product, x is related to y by r. We can write it this way. That's the notation we'll use. And x is related to y by r if and only if the ordered pair xy is an element in that relation. So you can think of it this way here. So the ordered pair xy is an element in the relation if and only if x is related to y. And then the set of all elements x in set x such that the ordered pair xy is an element of R for some y in set y is called the domain of R, the domain of that relation. And then the set of all elements in set y such that the ordered pair xy is an element of that relation of R for some x in set x is called the range of that relation. Couple comments here. So if you have this notation here, this means that x is not related to y by r. It has the slash through the r, so that means it's not related. And then in this definition, we're revisiting a function, but we're looking at it as a special type of relation. So we let x and y be sets, and a function f from x to y is a relation from x to y satisfying the following two properties. One, the domain of f is equal to set x, and two, for each x in set x, there is exactly one y in set y such that the ordered pair xy is an element of the function. So in other words, the properties are that every element in set x is related to some y in set y, and no element in x is related to more than one y in set y. Arrow diagrams. So we're going to let x and y be finite sets. We're going to suppose R is a relation from x to y, and then the arrow diagram for r is obtained as follows. You're going to represent the elements of x as points in one region and the elements of y as points in another region. We're going to draw like two separate circles, one for x, one for y. And then for each x, element x and set x, and element y and set y, you're going to draw an arrow from x to y if and only if x is related to y by r, by that relation. The arrow diagram defines a function if every element of set x has an arrow coming out of it, and 2, no element x has two arrows coming out of it that point to two different elements of y. Example 1, we're going to let x be equal to the set containing the elements 0, 1, and 2, and y is going to be equal to the set containing the elements 1, 2, and 3. Defining relation R from x to y as follows. For all ordered pairs x, y in the Cartesian product x cross y, the ordered pair x, y is an element of R, means that x is less than y. So this is like the condition that has to be met for the ordered pair to begin the relation. So for part A, we're going to state explicitly which ordered pairs are in the Cartesian product. So we're not even looking at the relation yet. We're just doing the Cartesian product between sets x and y. So for part A, x is the set containing the elements 0, 1, and 2. Y is the set containing the elements 1, 2, and 3. So if we're doing x cross y, this is going to be the set of ordered pairs, where the ordered pairs are of this form. So we're going to take the first element in x, 0, and pair it with each of these. So we're going to have 0, 1, then we'll have 0, 2, and then 0, 3. So those are three ordered pairs in the Cartesian product. Then we're going to take the second element in x, 1, and pair it with each of these elements here in y. So we'll have 1, 1, 1, 2, and 1, 3. Then we'll take the last element in x, 2, pair it with each of the elements in y. So you're going to have 2, 1, 2, 2, and 2, 3. So these are all the ordered pairs that are in the Cartesian product, the x cross y. That's our part A. And then part B, state explicitly which ordered pairs are in R. So we're looking at our ordered pairs, and if the x is less than the y, then it's in the relation. I'm just going to make a little note here. X has to be less than y. So for part B, the relation is going to contain, it's going to be the set containing the ordered pairs. 0, 1 is fine because 0 is less than 1. 0, 2 is fine because 0 is less than 2. 0, 3 is in the relation because 0 is less than 3. 1, 1 is not in the relation because 1 is not less than 1. But 1, 2 is in the relation because 1 is less than 2. Is 1, 3 in the relation? Yep. Is 2, 1 in the relation? No, because 2 is not less than 1. Is 2, 2 in the relation? No, because 2 is not less than 2. And what about 2, 3? Is that in the relation? Yes, because 2 is less than 3. So these are the ordered pairs that are in the relation, that are in set R. And then we're going to draw an arrow diagram for R. This is part C. So you're going to start with a couple circles or ovals. And then one of these, generally the one on the left here will be the first set of the Cartesian product. So that will be X. And then the other one will be set Y, the second set listed in the Cartesian product. And then this is relation R. So we generally do like an R between these, and then an arrow pointing from left to right because our relation goes from X to Y. And then X had the elements 0, 1, and 2 in it. And Y had the elements 1, 2, and 3 in it. And then you're just going to draw arrows representing each of these 6 ordered pairs that are in the relation. So you should have 6 arrows when you're done. So 0 gets mapped to 1, 0 gets mapped to 2, and also to 3. So there's going to be 3 arrows coming out of element 0 in set X. So these 3 arrows represent the 3 ordered pairs in the relation. And then you've got 1, 2 and 1, 3. So we're going to have arrows for those 2 ordered pairs. So 1 goes to 2 and 1 goes to 3. And then one last ordered pair, 2 gets mapped to 3, so an arrow for that. And then part D is RA function. So for part D is RA function. So the 2 things that had to be satisfied, each of the elements here in set X had to be used, right? Each of the elements in the domain have to be used. That is true. There's an arrow coming out of 0, 1, and 2. But you can only have 1 arrow coming out of all of those. So this is not a function because you've got these elements in X that are mapping to more than 1 element in Y. So this is not a function. Example 2, let A be the set containing elements -2, 0, 2, and B is the set containing elements 4 and 6. Define a relation S from A to B as follows. Given any ordered pair X, Y, and the Cartesian product A cross B, the ordered pair X and Y is an element of the relation S, means that X minus Y divided by 4 is an integer. All right, we're going to start by stating explicitly which ordered pairs are in the Cartesian product, A cross B. So A contains -2, 0, 2, and B contains 4 and 6. So A cross B will contain the ordered pairs -2, 4, -2, 6. Taking -2 here, mapping it with each of these elements. Then we're going to take the 0, pair it with each of these elements. So 0, 4, 0, 6. And then finally take 2, pair it with these elements. So 2, 4, and 2, 6. So those are all the ordered pairs in that Cartesian product. Now for part B, we're going to state explicitly which ordered pairs are in S. So this is like the condition that has to be met in order for the ordered pair to be in the relation S. So X minus Y over 4 has to be an integer. So X minus Y divided by 4 has to be an integer. So S is equal to, let's see, so this first ordered pair, that would be -2 minus 4 divided by 4. This would be -6 over 4. That's -3 halves. That is not an integer. So that's not going to be in a relation. What about -2, 6? So -2 minus 6 over 4. This would be -8 over 4. That's -2. That is an integer. So that ordered pair, -2, 6, is in the relation. What about 0, 4? 0 minus 4 divided by 4, that's -1. That is an integer, so that is in our relation. 0, 6. 0 minus 6 divided by 4, that's -3 halves. That is not an integer. 2 minus 4 divided by 4, that's going to be -1 half. That is not an integer. And then our last ordered pair, 2, 6, so 2 minus 6 divided by 4, That's -1. That is an integer. So that is in our relation. So we have 3 ordered pairs that are in the relation S. Part C, draw a arrow diagram for S. So here we have set A. Here we have set B. This is relation S going from A to B. And A contains -2, 0, and 2. B contains 4 and 6. And then we're going to draw an arrow for each of these ordered pairs in the relation in S. So -2 goes to 6. 0 goes to 4. And 2 goes to 6. So we have 3 arrows representing those 3 ordered pairs. And then the last part of this example is S a function? So part D, is S a function? So for it to be a function, each of these elements here, -2, 0, and 2, in set A have to be used. There has to be an arrow coming out of them. That is what's happening. And only one arrow can come out of each of those elements, which is also what's happening. So those 2 conditions are met. So this is yes, S is a function. So S is a relation that is also a function. Example 3. Let A be the set containing 2, 4, and 6, and B be the set containing 1, 3, and 5. Which of the relations R, S, T, and V defined below are functions from A to B? So for part A, we have relation R, and it contains the ordered pairs 2, 1, 4, 3, 2, 3, and 6, 5. So as a reminder, for a relation to be a function, these 2 conditions have to be met. The domain of the function is equal to set x, and for each x and x, there's exactly one y and y, such that the ordered pair x, y is in the function. Or it might be better, easier to think of it this way. Every element in x is related to some y in set y, and no element in X is related to more than one Y in set Y. So for part A, relation R is not going to be a function because of this 2 here. Okay, so R is not a function. It does not satisfy property 2. And you can describe this by saying that the ordered pairs 2, 1 and 2, 3 have the same first element, but different second elements. So you can describe it that way. Or you can say the element 2 in the domain is related to both 1 and 2. So that's how you can describe how that second property is not satisfied. So R is not a function. Part B. For all ordered pairs x, y in A cross B, the ordered pair x, y's in S means that y is equal to x plus 1. So for this, it might be easier just to start by listing which ordered pairs are in S. And A here contain the elements 2, 4, and 6, and B contain the elements 1, 3, and 5. So if you think of all the ordered pairs in A cross B, you're going to have 2, 1, 2, 3, 2, 5, 4, 1, 4, 3, 4, 5, 6, 1, 6, 3, 6, 5. All right, so let's see. Is this in there? Does 1 equal 2 plus 1? No. Is this one in there? Does 3 equal 2 plus 1? Yes, so that would be in S. Is this ordered pair in there? Yeah, just by looking at it, that's not going to be in there. This isn't going to be in there. This isn't going to be in there, right? In order for this equation to be true, y would have to be 1 more than whatever x is. This one would work, right? So that would be y equals 4 plus 1. Is this one in there? No. No. And is this last one in there? No, because 5 does not equal 6 plus 1. So we only have 2 ordered pairs in this relation. So then you have to think, are those 2 conditions meant in order for the relation to be a function? And no, S here is not a function. It does not satisfy property 1. So one way we can explain it is to say that not every element of that first set, so of A, set A, is a first element of an ordered pair. In S. So you can say it that way. You could also describe it by saying that the element 6 is in the domain. It's in set A, but is not related to any element. Right? Because property 1 says that the first set we have, that is the domain, and all those elements then have to be paired with something, mapped to some element in the other set. Part C, for all ordered pairs x, y, in the Cartesian product, the ordered pair x, y is in T, means that y is equal to x minus 1. So for this one, I'm going to go ahead and write it out like we did the last one. So A contains 2, 4, and 6, and B contains 1, 3, and 5, and y here has to be equal to x minus 1. So y has to be 1 less than x. So T is going to contain the ordered pairs 2, 1, and then 4, 3, and also 6, 5. So those are the 3 ordered pairs that are in T. So this is a function. T is a function. It satisfies both properties. Right? Because each of these elements in set A, which is our domain, are used. They are all related to an element over here, and they're only related to one element each. So it is a function. And then part D, V is defined by this arrow diagram. So is V a function? Maybe you want to try this one. Pause the video and let me know what you get. So in this case, V is a function. V satisfies both properties. Right? All the elements in set A, 2, 4, and 6 are used, and they're used exactly one time each. It's okay that you have this element here that's not being used. That's fine. It's still a function. Example 4, we're going to let both A and B be sets containing -1, 1, and 2. So we have equal sets there. And we're going to define a relation S from A to B as follows. The ordered pair x, y is in S, means that 1 over x minus 1 over y is an integer. So we're going to start by explicitly writing all the ordered pairs in the Cartesian product A cross B. So A is equal to B, which is equal to -1, 1, 2. So A cross B is going to be equal to these ordered pairs. -1, -1, -1, -1, -1, 2, 1, -1, 1, 1, 1, 2, 2, -1, 2, 1, and 2, 2. Okay, so that's part A. Part B, now we want to state explicitly which ordered pairs are in S. So it has to meet this condition. This has to be an integer. So 1 over x minus 1 over y is an integer. Okay, this would be an integer. When you plug these in, it would result in an integer. When you plug this in, that would result in an integer. When you plug these values in, that would not be an integer, because you'd end up having a 1/2 you're subtracting. And this would be an integer when you plug those in. This would result in an integer when you plug it in. This would not result in an integer because of a 1/2 involved. Same thing here, same thing here. This last one would be an integer though, because it would be 1/2 minus a half, which is 0, still an integer. So that one would be included. So those are the elements in this relation. And then part C is kind of just getting used to the notation. This means 1 is 1 related to 2, is 1 related to 1. So is 1 related to 2, and is 1 related to 1. So the first one, no, because there's no ordered pair 1, 2 in relation S. So 1 is not related to 2. You can put a slash through it. And then 1 is related to 1? Yes. 1 is related to 1. Part D is the ordered pair -1, 1 in the relation S is the ordered pair 2, 1 in the relation S. So is 1, -1 in the relation? Yes. Is 2, 1 in S? No. So you can say 2, 1 is not in S. Put the slash through it if you want. And then part E, draw an arrow diagram for S. So we have set A, we have set B, and this is relation S. Got -1, 1, 2 in each of these. And the ordered pairs that we had in S were -1, -1, -1, -1, 1, 1, -1, 1, 1, and 2, 2. So that's our arrow diagram. And then part F, last one, is the relation S, a function, and explain. So don't just write yes or no, actually give an explanation for these. So S is not a function. It does not satisfy property 2 because you can look at -1. That is related. -1 is related to both -1 and 1. And also you can look at 1 here. That is related to both -1 and 1. So you've got more than one arrow coming out of these two elements in set A. And then make sure you understand that a relation is a subset of the Cartesian product, and a function is a special kind of relation. And then that's it for this first section. So try the homework, and I'll see you in the next video.